Alright, hello ladies and gentlemen. So today's lesson will be first differences day 1. Obviously this indicates that we're going to spend another day working with first differences. But for today, our learning goals are to investigate the pattern in the first differences to determine if a relationship is linear or nonlinear. We will construct tables of values and scatter plots. For this lesson, you're going to want to either have a hard copy of the First Differences Day 1 worksheet, so you can go on the hub and print it off, or you can download it into a program like Notability on your iPad so that you can make your notes digitally. Either way, you're going to want to have that actual lesson note because otherwise there's going to be way too much to copy down. So, starting off, here we see 3.7.1 first differences, problem number 1. This is our lesson sheet, and this is the first example that we're going to work through together. We'll start by reading over the actual instructions. So, A. Jody works at a factory that produces square tiles for bathrooms and kitchens. She helps determine shipping costs by calculating the perimeter of each tile. So the information in this question is that we are making square tiles. The shape is going to be important. And we're also calculating the perimeter. Okay, so we're looking at the perimeter of square tiles. We see here that we have a table of values under part 1 where we are going to calculate the perimeter and record our answers in the perimeter column of the table. So, if we look at the perimeter here, we start out with a square that has a side length of 1 centimeter. If the square has a side length of 1 centimeter, the perimeter is going to be 1 centimeter by 1 centimeter by 1 centimeter by 1 centimeter. 1, 1, 1, and 1, for a total of 4 centimeters. Now if we look at the next side length, we have 2 centimeters. So 2 centimeters, 2 centimeters, 2 centimeters, 2 centimeters. So that would give us a perimeter of 8 centimeters. We'll continue and do this for each of the side lengths. So next we have 3 centimeters, 3 centimeters, 3 centimeters, and 3 centimeters, giving us a perimeter of 12 centimeters. Next we'll do 4 centimeters for 16 centimeters as the whole perimeter. And last of all, when we have side lengths of 5 centimeters, we'll take each of those sides, so 5, 5, 5, and 5. There's our measurements, giving us a perimeter of 20 centimeters. Alright, so we've completed our table of values here, which means that we now know what our perimeter for each of the different square tiles will be. Now that we've completed our table of values, we're going to look at our first differences, the major topic for today's lesson. When we take our first differences, we're going to find a relationship that exists between each pair of our dependent variable. So what we're going to do is take the lowest value and we're going to subtract the next value from it. In this case, we're going to take 20 and we're going to subtract 16, which is going to give us a first difference of 4. We'll do this again. So 16 subtract the number above it. In this case, it would be 12, also giving us 4. We'll next take 12 and we'll subtract 8 for an answer of 4. And last of all, we will take 8 and subtract 4, giving us 4. So we are asked to describe what happens to the perimeter of each tile when the side length increases by 1 centimeter. Well, we've already seen in our table of values that as we increase the side length, we see that the perimeter is going to increase. And our first difference has shown us that we will increase by 4 each time. So we can say that the perimeter increases by 4 when the side length increases by 1. And we know this because as we go from a side length of 1 centimeters to a side length of 2 centimeters, our first differences are 4. When we go from a side length of 2 to 3, we get a first difference of 4. When we go from a side length of 3 to 4, our first difference is 4. And when we go from a side length of 4 to 5, our first difference is 4. Meaning every time that we increase our side length by 1, we increase our first differences by 4. Next, we are asked to construct a graph of the perimeter versus the side length. Include labels and titles. So we're going to put this information on our grid, and we need to think about our perimeter and our side length. We need to decide on an independent variable or the measurement that determines the other. In this case, we can see that we have used our side length in order to determine the perimeter. That means that our side length is our independent variable and our perimeter is our dependent variable. So we're going to put our side length down along the x-axis and our perimeter along the y-axis. And so here we have our side length and our perimeter along our grid. I've used a scale of 1 for the side length because we're going to increase the side length by 1 each time. For the perimeter, I've had to use a scale of 2 so that I could fit all of the perimeter measurements along the y-axis. We need to get all the way up to 20, but we also need to be able to include a value of 4. So we've got our grid created. We're now going to put all of our points onto the grid. Our first is a side length of 1 and a perimeter of 4. Then we have a side length of 2 and a perimeter of 8. A side length of 3 and a perimeter of 12. A side length of 4 and a perimeter of 16. And a side length of 5 and a perimeter of 20. Now, for question A, we're asked which variable is the independent variable. Well, we've established that our side length is going to determine the perimeter, so that means our side length is the independent variable. And if our side length is the independent variable, for part B, which variable is the independent variable, we would have to say perimeter is our dependent variable. We're now asked to use the graph to describe the relationship between the perimeter and the side length. And we see that as our side length increases, perimeter increases. Last of all, we're asked to describe the shape of the graph, so we're going to put our line of best fit down and then describe what we see. We can see that when we draw our line of best fit, we go through all of our points, which would make this a linear graph. We're asked to calculate the first differences, which we've already done, and then we are asked, what do you notice about the first differences? Well, our first difference is 4 for each case. And when we get the same answer for all of our first differences, we say the first differences are constant. In this case, the word constant means all the same. Last of all, we're asked to summarize our observations. So, when the side length increases by 1 centimeter, the perimeter increases by 4 centimeters. The plotted points suggest a straight line. And our first differences are constant. Alright, so I would suggest pausing the video and making sure that everything for problem 1 is completed before moving on to problem number 2. Alright, here we are looking at problem number 2, or as it says on the sheet, problem B. In this problem, we're told that Jody is paid $8.50 an hour to calculate the perimeters. So she's paid $8.50 an hour in order to do the work we did for question A. We're going to start by filling in the pay based on the number of hours worked. So if Jody worked 1 hour, then she would make $8.50. Notice we don't put the dollar sign because it's already given to us up in the table. If we work 2 hours, we'd get another $8.50, giving us a total of $17. We will continue along. So if we work 3 hours, we will make another $8.50, giving us a total of $25.50. For 4 hours, we would make $34. And for 5 hours, we would make $42.50. We'll hold off on doing our first differences for now, and we'll complete the sheet in order. So it says for part 2 that we would describe what happens to her pay when the number of hours she works increases by 1 hour. And so we can say that when the number of hours increases by 1, pay increases by $8.50. For part 3, we're asked to construct a graph of her pay versus the number of hours she works. We need to include labels and titles. So we're looking at pay versus the number of hours she worked. And we're going to include labels and titles. First, we need to decide which variable is the independent variable. So we need to think about whether or not the number of hours makes your pay go up, or if the pay going up makes your number of hours go up. So obviously, for every hour we work, we make $8.50. That means that our number of hours would be the independent variable. And if our number of hours is our independent variable, that means our pay has to be our independent variable. Now that we've decided on our independent and dependent variable, we can make our graph. So when I set up my number of hours versus pay, I'm looking at how we increase for our number of hours, and we're going up by 1 each time. So I've just used a scale of 1 to 10. But for our pay in dollars, we need to go from $8.50 all the way up to $42.50. So I figured it's easier to just go by 5s all the way up to 50. We'll now put our points down and see how our graph looks. And so we can plot each of our points along the grid. 1 hour and $8.50, 2 hours and $17, 3 hours and $25.50, 4 hours and $34, and 5 hours and $42.50. We're going to draw our line of best fit, and then we will continue with part 3. So we've got our line of best fit there, going through all of our points. We can say that as the number of hours worked increases, our pay will also increase. So I know that there's not a lot of room on your sheet. If you want to write the relationship elsewhere and then just draw a line to part C, that's not a problem. Okay, I realize it's a lot harder to write all that in than it is to type it in. And last of all, we're going to describe the shape of the graph. Well, we can see that this graph is going to be linear. Alright. Part 4 asks for us to calculate the first differences in the first difference column of the table. What do you notice about the first differences? Well, first of all, we're going to have to actually do our first differences. So we'll take our two first difference values here, so $42.50, and we're going to subtract $34. That's going to give us $8.50. We'll do the same thing, so $34 minus $25.50. That's also going to give us $8.50. $25.50 minus $17 gives us $8.50. And last of all, $17 minus, minus $8.50 leaves us with $8.50. So there's our first differences completed. And if we recall, it asks us, what do you notice about the first differences? Well, just like in the first example, our first differences are constant. Alright, and this takes us down to the last stage, part 5, our summary of our observations. For part A, when the number of hours worked increases by 1, the pay increases by blank. Well, we know that for every hour we work, we're going to have our pay increase by $8.50. Our plotted points suggest a linear relation. And our first differences are constant. Alright, so just like before, I'd suggest you pause this video, make sure you have everything completed, and we'll move on to our last example for today. So for our last example, we are looking at question C. Raj, another employee at the factory, also works with tiles. He helps determine the shipping costs by calculating the area of each tile. Remember that the area of a square is length times width. So we're given our side lengths of 1, 2, 3, 4, and 5 centimeters, and we're going to do length times width. So if the length is 1, the width is also 1 in a square. 1 times 1 is 1. If the length is 2, the width would also be 2. 2 times 2 would give us 4. That's not very good. 4. There we go. 3 times 3 would give us 9. 4 times 4 would give us 16. And 5 times 5 would give us 25. In part 2, we're asked to describe what happens to the area of each tile when the side length of a tile increases by 1. Well, we can see that the pattern is not going to be that the area increases by a set amount. We're increasing by 1 the first time to go from 1 to 2, but our area increases from 1 to 4. When we increase our side length from 2 to 3, we increase our area from 4 to 9. When we increase our side length from 3 to 4, our area increases from 9 to 16. And when we increase our side length from 4 to 5, we increase our area from 16 to 25. So we're not going to be increasing the area by the same amount each time. Instead, we see that the area increases by a growing amount. So rather than try to describe this with a statement for every single area increase, I'm just going to say that as the side length increases, the area increases. We're going to find out what the relationship is as we move on, so I'm not going to worry too much about it right now. Question 3 asks us to construct a graph of the area versus length of the sides of the tiles. Include labels and tiles. Just as before, we need to find out our independent and dependent variable, and our independent variable is what determines something, so the side length determines the area. So we've got the length of the sides as our independent variable, and we've got the area as our dependent variable. We're going to label our graph, and then we're going to put in our points. So we've got our length of the sides in centimeters, and we've got the area in centimeters squared put on our graph. For the length of the sides, I've just counted up by 1 each time, but for our area, we need to go from 1 centimeter squared all the way to 25 centimeters squared. So I've skipped a grid each time, but I've counted by 5s. So this type of scale here allows us to put our points in pretty easily. It gives us a big space to work with, which is important when we're trying to plot these points. So our first point is a side length of 1 and an area of 1. We'll put that point in. Our side length of 2 has an area of 4. Our side length of 3 has an area of 9. Our side length of 4 has an area of 16. And our side length of 5 has an area of 25. We can see already that this isn't going to give us our straight line like before. Rather, it's going to be something kind of curved. Alright, so we're going to describe the relationship, and then we're going to also describe the shape of the graph. So just like before, we're going to use an as statement. As length of the side increases, the area increases. But when we're describing our graph, we can't call it linear because it doesn't go up in a straight line. Instead, we have to describe this as non-linear. Okay, so anytime that a graph does not create a straight line, we're going to talk about it in terms of being non-linear. Alright, next we're going to get our first differences. So we'll go up to our first difference table, and just like before, we're going to subtract the numbers from each other. We will take 25 and we will subtract 16, which will give us a first difference of 9. We'll take 16 and we will subtract 9, which will give us a first difference of 7. We'll take 9 and we will subtract 4, which gives us a first difference of 5. And we get our last first difference by taking 4 minus 1, giving us 3. Notice, these first differences are all different numbers. If our first differences are not the same numbers, we can't say that they are constant. Instead, we have to say our first differences are not constant. A nonlinear graph is going to give you first differences that are not constant. So, because our graph is nonlinear, we should expect to get this answer. Just like in the other two examples, when we had linear graphs, we did get constant first differences. Last of all, we're going to summarize our observations. So for part A, when the side length increases by 1 centimeter, the area increases by blank. Well, we've found that the area doesn't increase by the same amount. In fact, we found that each time that we increase the side length, the area increases by a larger amount. So we're going to say that when the side length increases by 1 centimeter, the area increases by a growing amount. By saying a growing amount, we are not making it seem that the rate of increase is the same, and we're speaking to the fact that this graph ends up not making a straight line, which we also would describe here as the plotted points suggest a non-linear relationship. So a non-linear relation. And last of all, the first differences are, as we've seen, not constant. And that is it for today. Okay, so make sure that parts A, B, and C are all complete. We are going to continue along with more examples in our next lesson, but for today, that's going to be everything. So, if you have any questions, please shoot me an email. If anyone does not remember, my email is maat@hwdsb.on.ca. Please don't email me copies of your lesson notes, okay? I don't need to see that. We're not going to be handing any of this in. You're going to have some questions to hand in after we finish the next lesson, okay? So for this time, all you have to do is complete this lesson, and if you have questions, then you can shoot me an email. All right? Take care, everyone, and we'll be meeting up again soon. Bye.